Okay, we'll go ahead and get started. Think all of you handed in your homework. And Logan, since you're attending remotely, if you can email me your homework like within the next little bit before I post the solutions online, I'd appreciate it.
Will do. It's going out right now. Thank you.
Okay, very good. And let's see. Administrative stuff. Yes, we are having class next week. Thanksgiving vacation doesn't start on Tuesday. And not having heard any strong objections from anyone, we are going to have our final exam on Tuesday, December 5th, which is officially the last day of class from 5:15 to 7:15. This room. So, and figure it'll be about half material from the midterm, half material since the midterm. Excuse me. And like before, the week before, I'll give you a little more details about the final. It'll be the same rules as for the midterm. Open book and open open note, open homework solutions, closed internet. So the rules will be the same. So the rules will be the same, just like before. And I think that's it for administrative stuff. So does anybody have any questions? Hey, so not well, and and for those of you attending online, the homework and the homework solutions will be posted. Will be posted tonight on Brightspace. So, anywho, so, so what we're going to do this week and next week is we're going to talk about a bit more practical topic. We've talked about stress intensity factors and the J integral and crack tip opening displacement. So now we're going to talk. So for this week and next week, we're going to talk some about how would actually go about measuring these values in the laboratory, and also some of the cautions to take in mind when you're doing some of these tests. So, because the idea is that the goal of these tests, and as we'll talk about, there are ASTM standards for them. The idea is that a lot of these values are considered to be fundamental material properties, like the critical stress intensity factor when a structure will fail. So the idea is to have coupon-like specimens that can measure some of these key values. So getting into it, so a fracture toughness test measures the resistance of a material to crack extension. So tests could yield either a single value of a fracture toughness or a resistance curve, an R curve, where the toughness parameters such as K or J, or the crack tip opening displacement, are plotted against the crack extension. And for materials that fail by cleavage, it's an unstable brittle fracture. A single toughness value is usually sufficient to describe tests that where the material mechanisms fail in that manner. And for cleavage fracture, it actually has a falling resistance curve. Now, conversely, other mechanisms that lead to a more ductile failure, such as microvoid coalescence, you'll end up with an R curve and a rising R curve. And the ductile crack growth can be stable, at least initially. We talked about, for the case of linear elastic and elastic plastic, the case of rising R curves. And when ductile crack growth, if you have ductile crack growth in a specimen, the specimen doesn't fail immediately. So you can quantify the fracture resistance either by the initiation value where cracking starts, or by the entire R curve to go through the whole process when you ultimately end up with your specimen breaking in two. And that's a lot of times, even in practical cases in design, it depends on your application, whether your design criteria is as soon as something happens, you consider the material not to be used anymore, or depending on your application and your loading, there's other circumstances where there's okay for things to progress for a while, and then you're ultimately only worried as that, like in the case of fracture, the structure breaks in two. The equivalent in a deformation analysis, sometimes you'll use the yield stress as the design criteria. As soon as your structure yields, you'll call it a day and say that it's outside of the bounds of your application. Or in other case, or in other applications or other loading conditions or situations, it's okay that you have yield and it's still usable as a structure and you're allowed to accommodate plastic flow, and you keep on using the structure and you design for the structure not for the yield stress but for the ultimate stress. So it's the same idea in fracture mechanics. You can quantify the resistance either by the point when you start to grow cracks at all, or if your situation is such that you have to or are able to have a more a more, for lack of a better word, forgiving uh, design criteria. You can say that it's okay if you have crack propagation and you're just interested in the point where the structure finally breaks into two pieces. Now, a variety of organizations throughout the world publish standardized procedures for fracture toughness measurements. The American Society for Testing of Materials, ASTM, is the big one you've probably heard about in this country. There's the British Standards Institution, the International Organization for Standardization, ISO, which you might have also heard about at some point. There's the Japan Society for Mechanical Engineers. And, usually, at least in this country and a lot of places even worldwide, the ASTM standards are considered the benchmark. And the first standards for K and J testing were developed by ASTM in 1970 and 1981, where the British Standards Institution published the first crack tip opening displacement test method in 1979. So the standards have been around for a while, and it's basically making other things when fracture mechanics started to move from a purely academic exercise to something that people got serious about using for design purposes. That's when the standards organizations got involved and started to come up with standardized tests and standardized methods to determine these critical values. So the existing fracture toughness standards include procedures for K1C, the KR curve, for linear elastic J1C, the JR curve crack tip opening displacement for elastic plastic, and this this section will focus primarily on the ASTM standards. They're the most widely used throughout the world, but the standards produced by other organizations are broadly consistent with the ASTM procedures and usually only differ in small details. And obviously, as technology improves and more experience is gained, the existing standards are continually evolving, because with all the various and sundry new test techniques and test methods, digital image correlation and all the various and sundry other testing technologies have been developed, the standards have been modified, and plus also as understanding evolves, like the also talk about, and we'll get into this, one of the pet peeves of the author of the book we're using is, in certain things, as greater understanding builds, as more experience is gained, the standards are modified. Now, for general considerations, the majority of the fracture toughness tests that we'll talk about have several common features. The design of the test specimens is similar in most of the standards, as we'll see, And the orientation of the specimen relative to symmetry directions in the material is always an important consideration because, and we'll talk about this just a little more in just a little bit, but the idea is even though the assumption always is that metal, particularly in metals are isotropic, and the assumption is that no matter what direction you pull on the material, the response will be the same. But in reality, due to the ways that metals are rolled or extruded or forged, a lot of times there's at least a little directionality in the response of metals. So the standards take that into account. And that's even something, even though we won't get into it, but it's even in terms of modeling, some in analysis. Sometimes if you find your analysis isn't what it expects, depending on the material you're looking at, could be that that there's orientation dependence on properties and responses that aren't accounted for in your analysis. And then obviously, if you're going to look at something like a composite where you have oriented fibers, then by definition, we're not going to get into testing techniques for nonmetals. But obviously, in something like a composite, the orientation dependence is critical because the materials are very much anisotropic. Now, the cracks in the test specimens are introduced by fatigue, as we'll talk about, although the requirements for fatigue loads vary from one standard to the next. And the basic instrumentation, and we'll just talk briefly about that, required to measure load and displacement is common in most fracture mechanics tests, but some tests require additional instrumentation to monitor the crack growth. So now fracture experiments can be grouped into two categories. I introduced this idea a little bit. Material tests and component tests. So the tests we're going to be talking about fall into the category of material tests. And we're going to basically go on the assumption that these parameters we measure are fundamental material properties. And full-scale tests of structural components are less common and usually don't follow a standard procedure. So as I said, we're going to be limiting our discussion to tests who the idea is to measure the fracture characteristics of the materials of interest. So here are 5 types of specimens that are permitted in the ASTM standards to characterize the fracture initiation and crack growth. Now, no standard allows all 5 of these configurations, and the design of a particular specimen type can vary between the standards. So the currently standardized are this one. This is the compact tension or C sub T. And this one here is this will come to a big surprise for you, a disc specimen. And this one here is the single edge notched bend. Again, no, SEB. And this one is the arc-shaped specimen. And then finally, this is the middle tension panel, MT. And also something to note is so these are the types of specimens that the various standards talk about. And also note that'll be important is remember for most of these types of specimens back when we did linear elastic fracture mechanics, we presented a whole bunch of tables to say the various ways to compute the stress intensity factor for all of these various and sundry specimens, because even for the homework I just handed out, basically just so everybody, just so everybody has it handy, I gave the section of the table that is representative for the compact tension specimen, because you'll be having to apply some of the things we talk about today to doing things with this type of specimen. Now, each of these specimen configurations has three important dimensions. We have our crack length, and we have our width, which is basically so the crack length, is by definition, the width is defined as from where we apply our load to the end of the specimen. And also, as we'll talk about, the crack length minus the width, basically, or the width minus the crack length, better way of putting it, basically defining the length between the end of the crack and the end of the specimen is also something we'll be looking at. And we also define the specimen thickness, which is specified by B. And in most cases, W is set to be twice, the width is set to be twice the thickness, and the A over W ratio is set to be approximately 0.5. We'll talk about that more in a little detail. Now, question or stretching? We'll talk about that a little bit, but just a little bit. The big thing we'll talk about is how you put the cracks in. As far as how you actually make the outer structure, that we're really not going to get into. Now, the vast majority of tests are performed on either the compact tension or the single edge notch bend specimens. And this cartoon below illustrates the profiles of these two specimen types, assuming the same characteristic dimensions. So assuming that the thickness and the crack length and the distance from the crack length to the end of the specimen are the same. Now, the compact tension specimen obviously consumes less material, but this specimen requires extra material in the width direction due to the holes, because we'll talk about you actually put rods in here. This is where the load is applied from, so you need extra material on the other side of the hole. And if you're testing a plate material or forging, the compact tension specimen is more economical. If you're looking at a specimen with a lot of welds, then the single edge bend specimen may be better because less weld metal is consumed in the orientation. Now, these holes here in the compact tension specimen is loaded by special clevises. So you put basically these clamps with these pins here that go through the holes, and and then you apply your load at the ends of these clevises, and then it's through these pins is how your load is transferred to your structure. Now, these compact tension specimens are usually machined in a limited number of sizes because a separate test fixture has to be fabricated for each specimen size. So the size includes, now, in terms of this variable t, where a 1t contact specimen has dimensions of thickness of 1 inch and width of 2 inches, which is why it's called 1. And obviously you can do it in metric also, and ASTM is converted to metric units, but the nomenclature has stuck. So there's generally, generally the standards have thicknesses of 1/2 inch, 1 inch, 2 inches, or 2 inches or 4 inches. Okay. Now, the single edge bend specimen's more flexible with respect to size. And the standard loading span for the SEB specimens is 4W, so 8 inches. And if the specimen is designed properly, the span can be adjusted continuously to any value that's within its capacity. So therefore, the single edge bend specimens with a wide range of dimensions can be tested with a single fixture. You can see here below in this cartoon that the constraints on the bottom for the 3-point bend, you can move these in and out depending on your load that's applied to make sure that you stay within the capacity of the load machine. Okay. Now, specimen orientation. Engineering materials are, as I talked about, engineering materials are seldom homogeneous and isotropic, and microstructures and thus the mechanical properties are often sensitive to direction. And the sensitivity to orientation is particularly pronounced in fracture toughness measurements because a microstructure with preferred orientation may contain planes of weakness where crack propagation is easy. So if you have a material where it's weaker in a particular direction, cracks and crack propagation tend to look for areas of weakness. So if it's really strong in one direction and weak in the other, well, in the direction where it's weak is where you're going to have cracks more likely to form and propagate. So since specimen orientation is such an important variable in fracture toughness measurements, all of the ASTM fracture testing standards require that the orientation be reported along with the measured toughness. And like anything official, ASTM has adopted a notation for this purpose. So here, this figure has the ASTM notation for fracture specimens extracted from a rolled plate or a forging. So you see here the rolling direction or the forging axis is kind of outside the plate. And you have, so that's considered the longitudinal direction. The regular transverse direction is in the direction perpendicular to the load. The short transverse direction is basically in the thickness direction, because the idea is you take this big plate and you could cut a whole bunch of specimens from it. So the short transverse is the thickness direction. The transverse direction is the width perpendicular to the loading direction. So as you can see here, when the specimen is aligned with the axis of symmetry, there's 6 possible orientation, and the letters L, T, and S denote the longitudinal, the transverse, and the short transverse directions relative to the loading direction or the forging axis. And you can see that 2 letters are required to identify the orientation of a fracture mechanics specimen. So it's kind of obvious from this cartoon, but the first direction indicates the direction of the principal stress. So like in this LT direction, you can see that that is designed so that the load will be applied along the loading direction. Where conversely, for this T-L specimen, you can see by the way the specimen's designed that the load would be applied perpendicular to the crack in the transverse direction, and similarly for this ST specimen, you'll apply loads in your short transverse direction. And the opposite, the second letter, refers to the direction along which the crack is oriented. So for the LT specimen, you can see that the crack is along the transverse direction. For the T-S specimen, the crack is along the short transverse direction. So the second letter will be perpendicular to the first letter, and which letters you use, it all depends on how the specimen is oriented. And with all these 6 combinations, you can pretty much capture all pretty much realistically capture all the combinations of loading directions and crack propagation to account for the variability. And a point we'll get to in just a bit is we'll cover it now, is that, well, first let's do this is, yeah, we talked about all this. And also, if you have round bars or hollow cylinders, you can do a similar type of idea where you have circumferential, which is C, radial, which is R, and longitudinal, which is L. So similar here, you have radial, which is along the radius, the circumferential, which is as much as possible with a flat specimen to kind of follow the circumference of the bar. And then you have the longitudinal, which in this case is basically up and down. So it's perpendicular. So it's along the axis of the bar. So it's the same type of idea. You have these various combinations of longitudinal, circumferential, and radial, and these various types of specimen orientations can pretty much cover the gamut, pretty much cover the range of all the types of combinations of material orientation and load direction to fully characterize the response of the material. Now, here's the caution, where due to the fact that we're dealing with the real world. Ideally, you should measure the toughness of a material in several orientations, but often this is not practical because you cut all of these and you do the test. First of all, it'd be a lot more tests, and then also depending on the dimensions of your material. For example, if you have a really, really thin plate that you're looking at, doing something in the thickness direction may not be practical. So you have to keep in mind the purpose of the test somewhat, and that trying to think what are the types of orientations and loading conditions that are of key interest in your material. And then, as I said, to an extent also the geometrical constraints by the material. If you have a really thin plate or a really short plate, it could make it non-realistic to do some of these orientations. Also, a low toughness orientation where the crack propagates in the rolling direction should be adopted for general material characterization or screening. But when the purpose of the test is to simulate conditions in a flawed structure, the crack orientation should match that of the structural flaw. So if you already know from how you're looking in your structure, or you have an idea where you've seen the potential of problems in a particular orientation and direction, then by definition, those should be those, and you see some initial flaws in the structure where cracks are going to be most likely to propagate. Those would be the cases where you would want to concentrate on doing your testing, where if there's certain directions where you don't notice a lot of flaws, that may not be quite as critical to test. And as I mentioned, geometrical constraints, but now that's the thing. Now, conversely, the low toughness orientation, so transverse to the rolling direction, is something where, because those are directions where the material is weakest, those are going to be your most likely orientations where you're going to have problems, because the material will be strongest along the rolling direction. But if you start pulling it transversely, it's a low toughness orientation, so may be more likely to have crack propagation. And as I said, geometrical constraints could also preclude testing in some configurations. If you have a real thin specimen, like the SL and the ST orientation, something with short transverse, well, if you have a real thin specimen where the short transverse dimension is real small, it's going to be awfully hard to do a test in this orientation. So these and the TS and the LS orientations could also limit the size of the specimen that you can extract from your plate. So in deciding on what testing you're going to do, somewhat it's the sense of, any test takes time and money, so you may not be able to always do all the tests you want, and then it's a combination of three things. If you see already that there's flaws and potential weak spots in particular orientations, you want to test those, because those could be critical. That's where the crack grows. You also you can do maximum and minimum cases. If you do in the transverse direction, that'll be a worst case. You do in the longitudinal direction, that'll be a best case scenario. But you also have to be realistic depending on the type of plate you're looking at, is that if it's a real thin plate, by definition, you may be limited as to some of the types of tests you can do. Okay. Now, in terms of the crack, usually you'll use, and you'll introduce notches by a milling machine with a sharp cutter or other types of machining processes, but that'll only get you so far. And to really do a fracture test, remember we talked about one of the big things with the fracture mechanics theory is that it applies to cracks that are infinitely sharp prior to loading. Where if you use a milling machine or something out, obviously this is exaggerated a little bit for effect, but you're going to get a big notch to start, which is not what fracture mechanics theory talks about. It talks about a sharp crack. So what you generally want to do is, through fatigue loading, you'll have this notch, and by applying fatigue loading in a controlled fashion, you'll get a little bit of a crack that initiates that fits in within the constraints of fracture mechanics theory, because you want it to be sufficiently sharp for the type of testing we're doing. So laboratory specimens invariably fall short, but you can introduce cracks that are sufficiently sharp. So as I talked about, this cartoon here illustrates that you put in your notch with your machine, and then you apply a cyclic load, which will initiate a crack at the tip of the notch, and it'll grow to a specified size, which is controlled by the level of the load you apply and how long you apply the cyclic load for. So, so as we talked about, you can introduce notches by milling machines with cutters or through other machining processes. And then modern day servo hydraulic test machines can be programmed to produce sinusoidal loading as long as other types of fatigue loading. Or available, there's also dedicated fatigue pre-cracking machines that cycle at a high frequency that are also available. So now the trick is that you need to introduce the fatigue crack in a way such that you don't adversely affect the toughness value that has to be measured. For example, if you're doing a test for K1C, the linear elastic fracture mechanics, you don't want to put in a crack that'll end up having a large plastic zone, because all of a sudden then it won't be linear elastic fracture mechanics. You also want to have the crack relatively small, crack radius relatively small, because that's the whole idea of doing the fatigue loading, is that you want something of a smaller radius than you'd get by putting in a notch with the machine. So cyclic loading produces a crack with a finite radius with a small plastic zone at the tip. So you have a little bit of strain hard material and residual stress distribution, but the idea is to keep it small. So to quantify this a little bit, so for a fracture toughness test to reflect the true material properties, your fatigue crack has to satisfy the following conditions. As I said, first, the crack tip radius at failure has to be the crack tip radius at failure has to be much larger than the initial radius of the fatigue crack. So you have to look at how the cracks which are going to be at fail, and you want to put in your fatigue crack such that the radius is small enough so that it has a long way to expand before it'll fail. And the plastic zone produced during fatigue cracking has to be small compared to the plastic zone at fracture. And the various fracture testing standards contain restrictions on the fatigue loads, which are designed to satisfy these above requirements. So for the precise guidelines depend on the nature of the test. For example, in a test for K1C, the maximum stress intensity factor that during fatigue loading must be no greater than a particular fracture of the critical stress intensity factor. And the standards talk about how to do this, and there's ways you can monitor these things while the test is being conducted. And conversely, for J or crack tip opening displacement tests, where the test specimen is typically fully plastic at fracture, the maximum fatigue load is defined as a fraction of the load where you get that yield, a fraction of the load at where you get yielding of that bit of material between the end of the crack and the edge of your specimen. Now, you can always perform fatigue pre-cracking well below the allowable loads in order to gain additional, to make sure that your results are valid, but the time required to produce the crack, the number of cycles you need to put the specimen through to get the crack, increases rapidly with decreasing fatigue load. So you use the standards as a guide, and then if you're really worried about things, you can always lower the load intensity that you put on the specimen to get your fatigue pre-cracking, just with the keeping in the back of your mind that the lower load you have, the longer it may take to get a good fatigue crack. But as I said, this is also all specified in the standards. So for instrumentation, so at a minimum, the applied load and the characteristic displacement on the specimen must be measured during a fracture toughness test. We showed a lot of examples of these load displacement curves. And you need additional instrumentation many times to can be applied to specimens to monitor the crack growth or to measure more than one displacement. And measuring load during a conventional fracture toughness test is relatively straightforward since nearly all testing machines are equipped with load cells. And the most common displacement transducer in fracture mechanics is the clip gauge shown here, which is shown in this figure below, where you basically put your gauges on either side of the notch and you monitor how the notch opens as you apply load, and you can, using some of the ideas we talked about, convert that to displacement. So this clip gauge, it's attached to the mouth of the crack. You have 4 resistance strain gauges bonded to a pair of cantilever beams. So you have your strain gauge on the top here and the bottom here, and top here, and and excuse me, and bottom here. And the deflection of the beams, so the deflection of these little beams here results in a change of voltage across the strain gauges, which varies linearly with the displacement. And the clip gauges are attached to sharp knife edges. You see these sharp edges here to ensure that the ends of each beam are free to rotate, because as your crack opens up, you want these beams here to be able to rotate as much as needed to capture the full displacement. And these knife edges can either be machined into the specimen or attached to the specimen at the crack mouth. Here you see an example, these little screws here where it's actually attached to the specimen. And so, and there's also a linear variable differential transformer, LVDT, provides an alternate means of inferring displacements in the fracture toughness test. So this figure here, this little cartoon here, shows the underlying principle of the LVDT, where you get a steel rod placed inside a hollow cylinder that contains these two tightly wound coils of wire. And when the current passes through this first coil, it becomes magnetized and induces a voltage in this second coil. And when the rod moves, the voltage drop in the second coil changes, and the change in the voltage varies linearly with the displacements of the rod. And this LVDT is useful for measuring displacements on the test specimen at locations other than the crack mouth. We've talked about before, there are times in some of the things we do where we're interested in displacements other than just at the far edge of the crack. And we talked about all this. And the potential drop technique utilizes a voltage change to infer crack growth, as shown here. So if you pass the current through the uncracked part of the specimen, the voltage increases as the crack grows, because as the crack grows, this area will get smaller, which means that the resistance will get bigger and the net cross-sectional area will decrease. And this potential drop method is another way you can plot voltage versus crack length and use that then to infer the growth of your cracks and also infer your displacements. However, the disadvantage of this method is it needs additional instrumentation. Now there's also an unloading compliance technique, which we don't have a cartoon for, that allows crack growth to be inferred from the load and displacement transducers that are part of any standard fracture mechanics test. And the specimen, and we've shown some graphs of this talking about some of the things in the theory, where we partially unload the specimen at various points along the test in order to measure the elastic compliance, which is related to the crack length. And as I said, we may go into this a bit later when we talk about the elastic plastic fracture mechanics. Now, in some cases, it's necessary to measure more than one displacement on a test specimen. You may want to measure both the crack mouth opening displacement and the displacement along the loading displacement along the loading direction. So this compact specimen talked about. Here we go. This compact specimen can be designed so that the load line displacement and the crack mouth opening displacement are identical, but these two displacements don't correspond in this specimen here. Because the mouth will be opening horizontally and the crack will be opening vertically. Where for the compact specimen, you're looking at kind of the same thing. So this figure here, back there. So this, so this figure here talks about, the type of setup you can have to simultaneously measure this crack mouth opening displacement and the load line displacement measurement. So the crack mouth opening displacement is inferred by the clip gauge attached to the knife edges, as we talked about. And the knife edge height has to be accounted for when computing the relevant toughness parameter. And you can also have this comparison bar attached here and attached to your LVDT, which can measure the load line displacement. And this is just one example of a variety of things which are available. So this comparison bars, the bar is attached to the specimen at 2 points, which are aligned with the outer loading points. And the outer coil of that LVDT we talked about is attached to the comparison bar, as illustrated kind of here. And this comparison bar remains fixed during deformation, where this central rod is free to move as the specimen deflects. So these are all specified in detail in the standards and some of the surrounding discussion of the standards. But the idea is that there's a variety of techniques available to measure the types of data that you need. So you need to look at the standard, you need to determine what is the key data you need, and then use the various methods that are available to measure the various values and displacements that you're interested in. Now, the last topic, and we talked about all this. So the last topic we'll talk about before break is that you can also put in side grooves to your fracture toughness specimen, and this figure here shows. And obviously this is exaggerated for effect, but the idea of the side grooving is to maintain a straight crack front during an arc curve test. Because if you don't have these side grooves, it's subject to crack tunneling and shear lip formation. Because way back when we did linear elastic fracture mechanics, we talked about the various You know, the shear lip formations and the various triaxialities that can take place during a K1C test. And we talked a little bit there about how crack grooving can avoid some of these problems. So the side grooves remove some of these free surfaces where plane stress conditions prevail, and if done properly lead to relatively straight crack fronts, which is good. We want our crack to just progress in a straight line. And typical side groove fracture toughness specimens have a net thickness that is approximately 80% of the overall thickness. If you make your grooves too deep, they'll produce lateral singularities, which will cause the crack to grow more rapidly at the outer edges because you're introducing concentrating factors here, which would cause your crack to grow. So you want a little bit of a side groove, but not too much of a side groove. So with all that preliminary, and I know it was a lot of preliminary, we'll take our break, and after our break, we'll start talking about the specific techniques to measure the critical stress intensity factor suitable for linear elastic fracture mechanics. So we'll start up again at about 20 after 6. Excuse me. Okay, we'll go ahead and get started. So, so as we've talked about before, when a material behaves in a linear elastic manner prior to failure, and the plastic zone is small compared with the specimen dimensions, the critical value of the mode 1 stress intensity factor, K1C, could be appropriate fracture parameter. And the first standardized method for K1C testing, ASTM E399, was originally published in 1970. And other K1C testing standards have been published throughout the world, but they're generally based on ASTM E399. And the standards undergone a number of revisions over the years, but the key provisions have remained largely unchanged for about the past 40 years. So the current version of E399 incorporates a number of improvements that reflects a 21st century understanding of the fracture toughness testing. For example, and remember this is one of the pet peeves of the author of our book, we talked about this before, is that in earlier versions of the standard, K1C was referred to as plane strain fracture toughness, and the phrase actually appeared in the title of the standard. And in the 1960s, we talked about, it was postulated that small specimens or thin sections fail under plane stress conditions, and plane strain fracture occurs in thick sections. And earlier versions of the standard reflected this viewpoint. And and in and for many years, it was taken as an indisputable fact that toughness decreases with increasing specimen size until a plateau is reached. And the original specimen size measurements and requirements in the standard were intended to assure that the K1C measurements corresponded to the supposed plane strain plateau. And there are number of assumptions that were not appropriate for the E399 standard. As we talked about before, finite element analysis of the stress state at the tip of the crack has shown that the effect of specimen size and fracture toughness is misleading, and it can be shown that the E399 test method, and we'll go over this a little bit, results in a size dependence in the apparent K1C that's the opposite of what conventional wisdom suggests. However, it's still a reasonably good test. So we'll now start talking about it in detail. So we just talked about the original title, standard test method for plane strain fracture toughness of metallic materials, is somewhat misleading. As we just talked about, the original specimen thickness requirements are a lot more stringent than they need to be to ensure predominantly plane strain conditions at the crack tip. And the real key to a K-based test method is to ensure that your specimen fractures under nominally linear elastic conditions, which means small plastic zones, particularly compared to the specimen cross section. So the important specimen dimensions are the crack length and the difference between the specimen width and the crack length, or the ligament length, and not so much the thickness. And in the revised version, the author of our book won, and the words linear elastic was inserted into the title, and the specimen size requirements focus on the in-plane dimensions rather than the thickness. So 4 specimen configurations are permitted by the standard. The compact tension is what we'll mostly talk about. The single edge bend specimen, the arc shape, and the disc shape specimens. And specimens for this test are usually fabricated with the width equal to the twice the thickness, but a range of width to thickness ratios are permitted in the standard. Excuse me. So for spend type specimens, which is the single edge notch bend and the arc shape, because going back to that figure Yeah, man. Before. You look here, the single edge notch bend, and similarly for the arc, they're more bending type of tests than they are just a straight mode one type of tests like here. So for these, back to where we were. Here we go. So for bend type specimens, the permissible range is for your W over B ratio to be between 1 and 4. And for the compact tension and disc shaped specimens, the W over width to thickness ratio can be between 2 and 4. And larger ratios can be used if the specimens are side grooved to maintain plane strain conditions along the crack front. And earlier versions of the standard didn't permit side grooving, and they set a very strict specification on width to thickness to be equal to 2. And in the standard, the specimens are fatigued pre-crack so that the crack length to width ratio lies between 0.45 and 0.55, and A over W is a lot of times just set to assume to be equal to 0.5. We'll talk about this. So most standardized mechanical tests, fracture toughness and otherwise, lead to valid results as long as all the procedures are outlined in the standard, but has to be monitored is that if the plastic zone at fracture is too large, no matter how good the technician is, it's still not a linear elastic test, which means that it's not a valid K1C test. So owing to the strict size requirements needed to achieve fracture under nominally linear elastic conditions, the standard recommends that a user performs a preliminary validity check to determine the appropriate specimen dimensions. So the requirement on the uncracked ligament length, so specimen says that the width minus the crack length, the uncracked ligament length has to be greater than or equal to 2.5 times the K1C over the yield stress squared. And to determine the required specimen dimensions, you have to make a rough estimate on the expected K1C for your material, and such an estimate can come from data for similar materials. And during the initial stages of the fatigue pre-cracking, the peak value of the stress intensity in a single cycle shouldn't be larger than 0.8 K1C. And as the crack approaches its final size, this maximum stress intensity factor should be less than 0.6 K1C. And remember, it's a maximum because we talked about in the fatigue pre-cracking, you're applying a cyclic load. So in order to make sure everything stays nice and linear elastic, to start off, you want, if you compute your stress intensity factor using this load, you want it to be less than 0.8 of what the critical will be. And then as you get closer to your final fatigue crack length, you put in stricter limits, and then you want this peak to be more 0.6 of the expected critical stress intensity factor. Here we go. And another note is that if you fatigue the specimen at one temperature and test it at a different temperature, your final stress intensity factor has to be, maximum stress intensity factor has to be less than or equal to 0.6 times the ratio of the yield stresses, because the response of metals is temperature dependent. You may just because it's easier to set up all your equipment, you may test it at a relatively low temperature, but then you may do your actual fracture toughness test at a high temperature. And at different temperatures, you'll have different yield stresses. So keeping that this K max is less than or equal to your ratio of your yield stresses multiplied by your expected K1C. This will again help to ensure that you're staying within the specifications of the test. And the fatigue loads requirements are less stringent at the start of pre-cracking, because when you first start your pre-cracking, you're far enough away from your ultimate end of your crack that the final crack tips remote from any damaged material that's produced in the early part of pre-cracking. So what goes on there is of less consequence, but the maximum stress intensity factor during fatigue must always be less than K1C, because you don't want, because even though you want to put in a crack so you have a nice sharp crack, you also don't want to put in so much of a load that you break your specimen before you actually do any testing for it. Now, obviously the chicken and the egg type of thing is that you need to have an idea of what K1C is going to be in order to determine the maximum allowable fatigue loads. And the user can specify fatigue loads based on what you think the anticipated toughness of the material is going to be. And like many other things, it's always good to be conservative. So be on the conservative side. So on one hand, you want to be somewhat conservative to make sure you don't want any problems. So as we talked about, you don't want to be overly conservative. Otherwise, pre-cracking could take a very long time. So it's one of these things where you want to strike that balance between being conservative enough to ensure that you have a valid test, but not so conservative that it takes forever to get your specimen set up just so you can do your testing. Now, when the pre-crack test specimen is loaded to failure, you monitor your load and displacement, and there's 3 types of load displacement curves that are shown here. Now, this PQ is your critical load that you use to determine your stress intensity factor. And it's defined in one of several ways, depending on the type of curve. On one hand, you can do this 5% secant line here, a line from the origin with a slope equal to 95% of the initial loading slope to determine and where this line intersects your load displacement curve, that's this P5. And for this case here, where you have a nice continually increasing load curve, that continually increasing load curve with just a little bit of non-linearity in here, where your 5% secant line intersects your load displacement curve, similar to the 2% offset stress for determining the yield stress, where this 5% secant line intersects your load displacement curve is determined to be your critical load in terms of the stress intensity, which is a little bit before you reach your maximum load. Now, this nonlinearity can be caused by plasticity, subcritical crack growth, or both. So for this type 1 curve, PQ is equal to P5. Now, with this type of curve here, this type 2 curve, you get a little bit of unstable crack growth, which occurs before the curve deviates from nonlinearity. So here, it's mostly linear, and then you do your 5% secant line, and it'll intersect here. So even though this is where your load curve intersects the 5% secant line, you're getting a little bit of, you have some unstable crack growth. So that's not and in the K1C test, we're interested just in stable crack growth. So in this case, the PQ is defined as the load at the point where you start getting that little bit of unstable crack growth. And then the extreme case is where you get failure of material before we've ever reached the point where you have your P5, where your 5% secant line intersects. And in that case, obviously, if you have failure before that occurs, the maximum load you reach is what's set to your PQ, your critical load. Okay. And talked about all that. So the crack length is measured from the fracture surface, and since there's a tendency for crack depth to vary throughout the thickness, the crack length is often defined as the average of 3 evenly spaced measurements. So once PQ and the crack length are determined, you can determine a provisional fracture toughness. So your provisional fracture toughness KQ is equal to your PQ times thickness times the square root of the width times your function of A over W. And this function of A over W is just what we talked about before and we did in all of our K1 discussions, where you look in the various tables that give your function of the crack length divided by the width for the various types of specimens, and whatever specimen you're using, that's the function of A over W you use. And this function of A over W is given in polynomial form in the standard for the four specimen types, and individual values are also tabulated in the specimen, or there's various tables that can be consulted for K solutions for a variety of configurations. Now, we talked about all the things that have to happen for a K1C test to be valid. So for a valid K1C test, all of these things have to be met. First, your A over W ratio has to be between 0.545 and 0.55. And we also introduced this before. W minus A has to be greater than or equal to 2.5 times your provisional stress intensity factor over your yield stress squared. And your maximum load, where your specimen cracks in two, has to be less than or equal to 1.10 times your PQ, defined on however you do. And as we talk, so these are the validity tests you have to check to see. And if you pass your test, then your KQ equals K1C, particularly if you also met all the restrictions on fatigue loads that we talked about before and limits on the fatigue crack curvature. So if you do all of that, then voila, this provisional stress intensity factor that you determined is equal to the actual K1C critical stress intensity factor. Now, as the size requirements are very stringent, so for many materials, it's often very difficult to measure a valid K1C. So you either have to have a high strength and low toughness or large test specimens for linear elastic fracture mechanics to be valid. So you have to see. So if you're in a material with low toughness or low yield strengths where you'll normally have a lot of plasticity, you have to keep in mind that if linear elastic fracture mechanics isn't valid, then things like the J integral or the crack tip opening displacement are what you need to define fracture, and we'll talk about that next week, how you do your tests to do the J integral and crack tip opening displacement. So just realize that you have these conditions, and depending on your material, you may or may not have sufficiently linear elastic response, and therefore you may need to incorporate elastic plastic fracture mechanics. But So you just have to be careful to see that if you careful to see if you fit or fit close enough the requirements that indicate you have a valid test. And there's a more recent standard that has an alternate test methodology, which basically combines K and J and CTOD all into a single standard. And previous versions of the standard provided a single test for all three parameters, but in order to eliminate redundancy with E399, the 2013 and later versions just talked about the test methods for J and CTOD. So the idea is that by combining E399 and E1820, you have a choice of post-test analysis procedures that cover the range of material behaviors. And if your test specimen has too much plasticity to compute a valid K1C, you can use J or CTOD to characterize things. And there's an ISO standard, which does combine the two ASTM standards to kind of be a one-stop shop to be able to realistically compute whatever parameter is needed to cover the state of your material. So a couple sample problems. We have a steel with a yield stress, and we're given an estimated K1C. So given these conditions, and the author put this sample problem is because I'll show you right now, it kind of proves the point he's trying to make for a relatively low yield stress. So estimate the dimensions required. So W minus A is greater than or equal to 2.5 times your KQ divided by your yield stress squared. So for this case, it's equal to 2.5 times 200 divided by 350 squared, which is equal to 0.816 meters, which obviously you're not going to do a test with that, because also if you have A over W is equal to 0.5, W would then be 1.63 meters, which you're not going to do a test like that. And your required specimen thickness then is thickness B is equal to 408 millimeters. So if you put in side grooves, and so all this. So if you put in side grooves, you could reduce the thickness somewhat, but a large specimen would be required for a K1C test in this material. And for this material, estimate, and if we specify W minus A is equal to 10 millimeters, 25 millimeters, or 50 millimeters, which are more realistic, then we can take that same equation that we just showed and manipulate it to get K1C, valid K1C. So for the first case of W minus A is equal to 10 millimeters, K1C is equal to 350 times the square root of W minus A of 0.01 meters divided by 2.5, which is equal to 22.1. For W minus A is equal to 25 millimeters, which is about an inch. You have K1C is equal to 350 times the square root of 0.025 divided by 2.5, which is equal to 35. And then finally, for the W minus A is equal to 50 millimeters. You get K1C is equal to 350 times the square root of 0.05 divided by 2.5, which is equal to 49.5. So in the homework you've been gotten, you basically are going to be doing all kinds of exercises where you take these various conditions and use them to draw some conclusions about the K1C or the validity of tests or other things involved with that. So these problems here are basically manipulating these equations is basically what you're going to be doing for your homework that I just handed out. Okay. So limitations of the E399 and similar standards. So we talked about before the conventional wisdom regarding the effect of plate thickness on the fracture toughness, and that at first when they first developed these things, they talked about transitioning from plane stress fracture to plane strain fracture. But as we also talked about, in reality, it's a competition between the slant fracture, where you have the fracture on the 45-degree plane, and the flat fracture, where the fracture plane is normal to the applied stress. So we talked about normally in your specimen, you have these areas on the edges where it's a slant fracture, and in the middle where it's a flat fracture. And in thinner specimens, the apparent fracture toughness is higher because the slant fracture dominates. And this figure here shows the effect of the specimen thickness on the KQ in a titanium alloy, along with the original thickness-based size requirement. And in this case, the ligament length was fixed while the thickness was varied. And if you look at the actual data, you see that the toughness reaches a plateau where the thickness divided by W minus A is greater than 0.2. So the original thickness requirements, proved to be not so valid when you look to actual materials. And the reason for that is, particularly as you move from flat fracture to slant fracture, you get an R curve that significantly increases. And the R curve for slant fracture is significantly steeper than that for flat fracture. So the effective R curve for a specimen that has both slant fracture and flat fracture will fall somewhere between these two extremes, because this initial requirement assumed you had all flat fracture. This curve here is mostly in the case for the aluminum, where it's mostly slant fracture. So if you have a material that's halfway halfway in between, it will be, crud, okay. Yeah. So fall somewhere between the extremes. So yeah, affects the KQ. So the relative amount of slant versus flat fracture affects the KQ value measured according to the E399 procedure. If you have a side groove specimen, it eliminates the shear lips and enables the R curve for flat fracture to be determined. And the standard's been revised to allow slide grooves. And by putting in shear lips, you can eliminate them with the slide grooves. But if you have a rising R curve, you have, by the E399 size requirements, again, you have the increase in your R curve. So this is KQ. So once again, this is the KQ versus W minus A for an aluminum alloy. And the measured toughness actually increases with specimen size, which is you don't want for a size-independent material property criteria, which runs counter to the conventional wisdom. And this effect can be understood because in this type 1 load displacement curve, which is typical by crack growth, we define PQ as the point where the curve deviates from linearity by by 5%. And if the nonlinearity is primarily due to crack growth, then this deviation from linearity corresponds to crack extension through 2% of the ligament. So the specimen size effect, we can see that if you have increasing ligament length, you have increasing R curves, which affects what you measure and determine for your KQ. So this figure illustrates the size effect when it's based on 2% relative crack growth. Now, if the R curve is insensitive to specimen size, then specimens with larger ligaments will result in higher KQ values because the measuring point is farther up the R curve, and the relative steepness of the R curve governs the magnitude of the KQ size effect for materials that experience ductal crack extension. So the 399, so the flatter your R curve is, the more that the 399 procedure will result in toughness that truly is independent of size. And the original authors were aware for the potential of size effects, but so what they did, they put that's why they put that maximum of 1.1 on the P max to PQ ratio, because it reduces the size effects because it excludes materials with a steep R curve. So if you have an R curve that follows a power law extension, such that your R curve is equal to A times the change in your crack length to some constant N. A and M are material constants. So by using this and assuming the nonlinearity is due entirely to crack growth, it is possible to compute the P max over PQ ratio for standard test specimens. And if you do that, you get figures like this for your compact specimen. So your load ratio then becomes a function of the exponent M, but it's insensitive to A over W. You see that it's relatively flat. And this analysis also predicts that the ratio of P max over PQ is completely independent of W. Now, these restrictions are only satisfied for M less than 0.1. For M above 0.1, you get a much higher line on the curve here. So ASTM 399 is applicable only to materials with relatively flat R curves. And so if you have materials that you have nonlinear, so if you have materials that fail by fractures such that the nonlinearity is due to plastic zone formation as opposed to stable crack growth, the 5% secant method is obviously totally inappropriate for estimating fracture toughness. So instead, the load at which unstable crack growth occurs should be used to compute the toughness. And if the nonlinearity in the load displacement curve is small, the fracture load can be substituted in these equations we talked about earlier to compute KQ. And so, but still, if there's significant nonlinearity due to plastic deformation, you should characterize the toughness by J or CTOD, which we'll talk about next week. And the key advantage, at least for this author, the key advantage to generalized test methods is that they allow for both elastic and elastic plastic material behaviors. And also, we won't talk about this, but if you have ductile brittle transitions, there's also a statistical size effect which could cause problems. So it's a legitimate test. There is a standard. I'm not quite as gung-ho as the author. I'm more the idea that there are issues and potential limitations, and you just have to be aware of it when you do the tests to determine the properties of your material. So we talked about before, materials that fail by microvoid coalescence usually exhibit a rising R curve. And the test method, the 399 test method, measures a single point on the R curve, and thus it contains an inherent size dependence on the toughness because the point on the R curve at which KQ is defined is a function of the ligament length, as we talked about in this figure here. So as an alternative to measuring a single toughness value is determining the entire R curve for materials that exhibit ductile crack extension. And there's another ASTM standard, E561, which outlines the procedure for determining K versus crack growth curves in such a material. And unlike the original test method, the KR standard doesn't contain a minimum thickness requirement and thus can be applied to thin sheets. This standard, like anything else with linear elastic fracture mechanics, is appropriate only when the plastic zone is small compared with the in-plane dimensions of the test specimen, and this test method is often applied to high-strength sheet materials. And thin sheets generally have a steeper R curve than thick sections because the slant morphology dominates in the former. If you have a thin sheet, you have lots of area with slant fracture and just a little bit with flat fracture. And the effect of the section thickness on the shape of the R curve, according to the author, a lot of articles say that the thick sections exhibit a single value of K1C while the same material displays a rising R curve. And this whole bit about whether it's plane stress fracture or plane strain fracture. And the thickness has an effect on the crack tip stress state, which does affect the slope of the R curve. But there are also some materials that have a rising R curve even for flat fracture under predominantly plane strain conditions. But so the only instance where a thin section may have a rising R curve while a thick section has a flat R curve is where the difference in the crack tip triology causes a fracture mode change from ductile tearing to cleavage. So this figure illustrates the typical KR curve for a predominantly linear elastic material. And at first, it's very steep, and we talked about this when we first introduced the R curves. As little or no crack growth occurs with the increase in the stress intensity factor, but as the crack begins to grow, the stress intensity increases with crack growth until you reach the steady state point where your R curve becomes flat. So you can also define the critical stress intensity factor as this point where the driving force is tangent to the R curve. And this instability point is not a material property, though, because the point of tangency depends on the shape of the driving force curve, which is governed by the size of geometry in the cracked body. So under a laboratory specimen under load control, then in this case, Kc could also correspond to Pmax in a type 1 load displacement curve. And such a Kc value would exhibit size dependence similar to that for KQ based on the 2% crack growth criteria, as we talked about as shown here. So the big thing from this is sometimes, depending on your load conditions, and like true for many other things, you measure things in the laboratory, but they may not necessarily be transferable to full structures because what happens in your structure, you have a different situation. You have a much wider area and different loading conditions than you have for very controlled conditions in the laboratory. So that's what we have for today. And as I said, your homework, you'll be playing around with all this in detail. So what we'll do next week is we'll finish up our discussion of the KR, testing for the KR curve, and then we'll also talk about how to do testing to determine the J integral and the crack tip opening displacement. So there's nothing else. Have a good week, and I'll see you guys next week.